kg.
A k, on the operator ILZ, the kz is a operator of a different spin, doesn't act on it.
Yeah, but how about if you apply ILG first, then apply IJG second?
On kz or ILZ,
Yeah.
commutes,
See.
doesn't do anything.
Why you didn't say 2ILZ outside the parentheses equals 1? So you have different
No,
formula
not two.
result.
Two. You get two. Two. This is stuck. Okay, that works. Yeah. You see, there is a 2 IKX ILZ. I have taken 2 ILZ here,
Yeah, that can be
and
1.
I get another 2 ILZ here,
Yeah.
and the 4 ILZ square is gives me 1.
Yeah, but you can also say 2LZ, 2ILZ is equals 1, and the parenthesis is the result.
2 ILZ is not equal to 1. 2 ILZ square is equal to 1. 4 ILZ square. LZ square is equal to 1 by 4.
Yeah.
I
But ILZ equals 1/2.
No. That's an operator.
Okay.
I z square. It goes back to the eigenvalues.
Okay, it's 1/2 and minus 1/2.
I square is equal to. What should I say? Is 1. Oh, what did I do? Okay, that is the eigenvalue, and so Iz is 1/3 of that. Okay, from there you get it. Ix is 1/3 of that. So Ix square is equal to Iy square is equal to Iz square is equal to half, 1 by 4. That's it.
That's right.
Yes. Okay. Okay. So we know now that if we this antiphase X magnetization, antiphase with respect to spin L, will give us a component which is still antiphase X magnetization, antiphase with respect to L, but will also give us a Y magnetization of spin K. Similarly, you can see this and this one. Actually, one can then write them down in the form of a rotation in the operator spaces of these operators. For example, IKX, this form a subspace, a Cartesian subspace, IKX, IKY, ILZ, IKZ, ILZ. Okay, and they represent a rotation in this subspace. J evolution represents a rotation in this subspace. And you can rotate about IKZ, ILZ, or you can rotate about IKX, and you will get from one this to this, or you can rotate about IKY, ILZ, and you will get from one to the other. Okay, and so this picture here is very helpful. You don't have to write many formulas. If you have the picture, you can use it. And similar pictures can be formed for these operators. What here it is, IKX, IKY, IKZ, with the ILZ term in multiply in these two. Here it is IKX, IKY, IKZ, with LZ term multiplied to KX and Z. And the similar corresponding operators for L. Okay. One formula which I don't know why I have written here at the moment, which I sometimes I don't know where I will use it, but it's a very interesting formula. I had quite a lot of trouble with it one day. Is this formula? Please note it down, or you have it noted down, but remember it. What it says is that if there are operators like this, IKX, ILX, and you want to see the commutator with IKY, ILY, okay, they commute with each other as for spin half, only for spin half. The anti-commutator, which is valid for spin half, is the one which you have to use it for proving this formula. And so this is a very useful formula. Now we have seen what happens in chemical shift evolution, we have seen what happens in J evolution, and we see what happens in pulse evolution. That's rather simple. Pulse evolution very straightforward. And since all these are if it's just new, then they commute with each other. They are just sum of different spins, and they commute with each other, and you can apply it any order I like, and that's fine. Okay. What I'm basically saying here is, suppose you have here is like I beta I1x plus I2x. Then I can say I1x first, and then calculate that, and I can do with I2x afterwards, or I can switch them. It doesn't matter, because some over spins here. If it was some over new, then it will not be true what I'm saying. New is x, y, z components. And so it's straightforward. IKY rotates and gives me IKY cos beta plus IKZ sin beta. If it's a z component and I'm applying a pulse on, say, for example, x-axis here, then it will give me IKZ cos beta. So what basically it's saying is that if you have a y component and you're applying a pulse along x-axis, then you'll get a cos y component and anti-clockwise, so plus z component with sin beta. And if you have a z component to begin with, applying a pulse along x-axis and do anti-clockwise rotation, you get a cosine component of the z and minus times sine component of the y. And you can do it with x or with y. Basically, we apply RF pulses either along x-axis or y-axis. And these are the only two we need. Okay. All right. And what does it do to these operators? To the single spin operators, it is straightforward. And if you have IKX, that and you apply a pulse along x-axis, nothing happens to it. If you have an IKY operator, you apply a pulse along y-axis, nothing happens to it. Okay, that anyway you remember. But now if you have these multiples, like IKX, ILZ, and you apply a 90-degree pulse along y-axis, okay, so we get IK, okay, let's apply the pulse along y-axis, and I can do it in 2 steps, or in 1 step, this is okay. The K spin will go from x to y-axis and x to minus z, okay, x to minus z. And L spin will go from z to plus x. So I will have a minus IKZ plus ILX into plus times ILX. And what has happened here is what we have already discussed before, that this is the magnetization of the spin, x magnetization of spin K antiphase with respect to L. And we get x magnetization of spin L antiphase with respect to spin K. And this is the coherence transfer step. And I have stated it again that one quantum coherence of spin K antiphase with respect to L and transfers the coherence to another spin and gives me one quantum coherence of spin L antiphase with respect to spin K. What happens if we apply, instead of a y pulse, a x pulse to the same operator? Okay. And you see, the x pulse commutes with the x part and doesn't do anything to it, but it rotates the z component into y component. So I get twice IKY, ILY, IKX, ILY, and this is the 2 quantum coherence of spin K and L. It has contains both 0 quantum and double quantum. It is a 2 quantum coherence of spin K and L. So depending upon whether we apply this pulse along x-axis or y-axis, the result is x-axis or y-axis, the result is dramatically different. This is a very important step here. And if this is clear, then I'll go further. Maybe I pause a minute and ask you a question. Any questions?
So you express the density operator in terms of this operator?
Yes, we express the density operator in terms of this in this basis set.
And how do you decide you observe the signal?
Okay, we are going to take a trace of the density operator with I minus. You can say IK minus or IL minus. Or you can say IKX and ILX. Then you are detecting both plus and minus component, and you are looking at both plus quadrant and minus quadrant in a 2D experiment.
What you do is you just apply the pulse and then calculate the density matrix and get the matrix.
That's right. That's our procedure. Our standard procedure is to find out the equilibrium density matrix, apply pulses, go through this time evolution. At the end, we have the density matrix and detect it with a detectable operator and take the trace. And this is our procedure for calculating the result. What we have simply done is we have expressed the density matrix in the beginning in terms of this basis, and we just see how these operators evolve, and we would have to take the trace in the end, but we already know how these operators look like, what result they will give me. And so we don't have to calculate anything.
And what's the frequency difference between the single quantum and double quantum and triple quantum?
Frequency difference.
Is Raman frequency?
Okay, yes, it's a Raman frequency difference, but when you do demodulation, it is only the offset which gets added up. I should have said that in the multiple quantum lecture. Okay, we talked about it as if we just completely ignored the Raman frequency. We only looked at the offset dependence. For example, if you had one transition, I showed you a multiple quantum spectrum of a two-spin system. This is the single quantum part of it, and a zero quantum which came and gave a line. This, let me call this nu A and nu X or nu B. Okay, and this is with respect to some arbitrary zero I talked about. And this zero is actually our demodulation frequency, the frequency at which we do demodulation.
Carrier frequency?
Carrier frequency, for example. Okay.
And where is the then double quantum?
Okay, and the double quantum should come at twice the Raman frequency plus nu A plus nu B.
Yes.
In the laboratory frame. But in the rotating frame, we have to subtract twice the Raman frequency also for the double quantum. So a demodulation that we do at Raman frequency looks a double Raman frequency for a double quantum and triple Raman frequency for triple quantum. And so the double quantum comes at nu A plus nu B. In the lab frame, it will come at nu A plus nu B plus twice omega naught.
So you need two times of the modulation frequency.
But it's automatically demodulated at that frequency. Okay, so we just get an offset sum.
The receiver get the, I'm sorry.
Okay,
Receiver.
This comes at nu A minus nu B. And the triple quantum, if you had a triple quantum, in this two-spin system you don't have a triple quantum, but if you had a triple quantum, will come at nu A plus nu B plus nu C. And you have to only worry about the offset from the carrier. And the whole Raman frequency, actually it is a twice Raman frequency. In the laboratory frame, if you look at the element in the density matrix, it is evolving with twice the Raman frequency or thrice the Raman frequency.
Then how the receiver can detect that frequency?
Okay, it doesn't detect it directly. We transfer it into a single quantum coherence first. And so it doesn't detect directly.
So what you observe? You observe the free induction decay or
Yeah, we do indirect detection in the two-dimensional experiment. In the last lecture, we talked about it. Yeah.
So it's not just single experiment?
Now it is not a single experiment. It has to be a two-dimensional indirect detection experiment.
Thank you.
Okay, we are through to this point. Here it is a detail which maybe it's We don't have a problem. All right. I mean, I don't mind staying here longer than what the time given is. Stop me whenever you think you can't take it anymore. I should have brought your slide, Charles, today. Maybe I'll bring it tomorrow and say that's too much. Okay, what happens if you have a pulse with an arbitrary phase? Okay, that is, I apply RF pulse along this direction rather than X or Y only. Okay, I mean, I can apply a pulse along any axis I like. And this is very simple. We just represent this as a rotation about z-axis by angle phi of the operator ikx. And this is formally, I can break up the result of an experiment calculation with a RF in this direction as if it is a rotation about of x operator about z-axis by an angle phi. And I have these three operations to be done, one after the other. Okay, and the phase shift beta, I had a lot of things to say about phase shift, but anyway, I will not skip all that stuff and just mention to you the mathematics part of it. A phase shift is a delay, but I don't have time to go through the delay part of it. I'll tell you a story about it. In any case, you can do it either by the delay line, which is or a phase shifter that nowadays digital phase shifters come in the machine, or you can also cook up a phase shift by applying a pulse sequence like this. Okay, and the pulse sequence is basically copying the idea, and the phase shift comes as an angle of the Y pulse. And you can work it out yourself. It's straightforward. A phase shift is a rotation about z-axis by angle beta, and you can cook it up like this. And this gives you RF pulse, RF phase shift. What I could fix. Now we use these things now. We come to the using. So far we have developed the formalism, and we come to the use. And one of the sequences which is very useful, we often use this sequence in which we suppress the chemical shift evolution and let the J evolution be present. And this is done by the help of the sequence. And if you have a KZ operator present here, and we apply this pulse sequence, where it's a pi by 2 Y pulse, pi by 2 X pulse or Y pulse, and here on L spin also. Particularly in heteronuclear shift correlation, we did this. Then we see that we have starting from a IKZ here at this point, a 90-degree Y pulse transforms into IKX. And now I directly write the evolution at this point, up to this point, because I know the chemical shift is focused in this case. Okay, and so I write the J evolution, and J evolution is IKX cos pi j plus twice IKY ILZ sin pi j. And if I match this tau to the J coupling in such a way that tau is equal to 1 upon 2J, then you see I will have only this cos 90 degrees being 0, sin 90 is 1, and so I will have only this term left. And so I get this term. So this sequence up to this point transforms a IKZ into a IKY ILZ. Okay. And a 90-degree pulse, Y pulse on K and L gives me a 2-spin coherence. On the other hand, a 90-degree X pulse on K and L give me the coherence transfer from K to L. Let's see what happens. What is if I don't want to write these two pulses and I want to see the evolution under a sequence tau pi tau. I have a mistake here. I should have had a IKX there. I think in the notes is something else. It's a IKZ there. Z makes no sense. It's a rotation about axis. Okay, and the result would be this. But if we'll get a additional statement here which says there's a pi pulse which is causing a chemical shift term, focuses but with a minus sign. Okay, that term comes before J evolution, and you can see that really I have a proof here which shows that this term will be present. Usually, basically gives a minus sign to the operators, nothing else, but minus sign to the Z and Y operators and nothing to the X operators. And this term should be remembered. Often people forget about this term. This is an interesting sequence. We have actually already used it in a previous, yes, I think we did. Okay, in the bird sequence I have written down there, I've used this, but we didn't go through the bird sequence logic. All right, this is a sequence which is here X and X here, all of the same phases, 90, tau, pi, 180, tau, 90 sequence. And I have broken it up into various parts, and finally in the end, this whole sequence looks like as if I am rotating by a double operator, IKY, ILY. Okay. The result of the sequence is